Yeah, so now we will discuss from this point onwards. So what are the challenges in using FPGAs for CNNs? So first thing is FPGAs usually don't have so many resources what a GPU has. For example, so LNet 5 is one of the old CNNs, right? It was proposed in 1990s. So you can see that is really old. So second layer of LNet 5 requires 2400 multipliers, which cannot be provided by most FPGAs. So the point is, you have to reuse the hardware. That means if you have only 24 multipliers, then you have to use those multipliers 100 times. Okay. Further, the bandwidth of FPGA is less than that of GPU. So this 20 is just a number. Probably, I think in recent ones it could be a little higher. But even then, definitely the FPGA bandwidth is much lower than that of the GPU. So further, so FPGAs have only small memory capacity, on-chip memory capacity. Okay, so if LXNet has more than 60 million parameters, if you store them in 32-bit single precision format, it will require around 240 megabyte of storage space. So that means you can't store the entire LXNet model on chip. You have to store it off chip, that means in the DRAM. And as you do the computation, you fetch those data elements into the on-chip memory. And there are other networks which have even higher memory requirement. Okay. So here you can see VGG16 has high number of, it has, so workload, GOPS means how many computation it needs. So that is also high for VGG, and circuit size is proportional to the amount of gates. So that is also high for VGG16. So VGG16 requires a lot of computations and it has a lot of number of parameters. Whereas there are other networks which have fewer number of weights and fewer number of computations. Okay. Now, once you are storing these parameters at off chip, and when you're doing the computation, you need to bring them to on chip, right? That incurs a lot of performance and energy overheads. So you want to reduce off-chip accesses by using on-chip memory, but on-chip memory is very limited. Okay, on-chip memory is limited. For example, these are different FPGA models. Okay, these are names of different FPGA models. Okay. So this is their register file storage capacity. This is the SM storage capacity. Fine. So this is one of the high-end FPGA. So you can see only the high-end FPGA, this VU9P, only this can hold SqueezeNet entirely in its on-chip memory. And that is also because SqueezeNet is so small. Okay, this is, whereas other networks which are really large, SqueezeNet is really small network, just like MobileNet, MobileNet, ShuffleNet, GoogleNet, SqueezeNet. These are the example of compact networks which have very few parameters. So their parameters can be stored in the on-chip memory, but these larger networks cannot be stored entirely in the FPGA, in a single FPGA. So these limitations pose severe design constraint. So full enrolling is not possible. So that is what I explained. Suppose if you have suppose 24, if you want to perform 2400 multiplications, if you had 2400 or higher number of actual multipliers, you can do all of those 2400 multiplication in a single go, right? That is called full unrolling. But because you don't have 2400 multipliers, suppose you have only 24, then you need to fold it. First fold, you do only 24. Next fold, again do 24. Next fold, again do 24. Like this, you have to do it in 100 times. That will bring the total of 2400 multiplication operations. That is called unfolding. That is called folding, temporal folding. Now, this presents challenges in achieving efficient data layout. Why? Because, see, you are first doing only 24 multiplication, then 24, then 24, then 24. But while you're doing next set of 24, where do I store the result of first 24 operations? I need to store the result somewhere, right? So that's the idea. We need to store those results somewhere and then process it. Okay. So, so that requires a lot of routing, storage decisions, and so on. So here, this is some table comparison of BG16. So these are the two classes of FPGA. This is one Zynq FPGA, another is UltraScale FPGA, and these are different research papers: FPGA Format, DNN paper, Angela, Kathy. Actually, you don't have to remember. I'm trying to give some numbers also, apart from the research insights. Also, we are trying to discuss some numbers. So here you can see these researchers, they have implemented their accelerator on this FPGA, which has 125 megahertz frequency. So you can see frequency is quite low. Then this is the how many LUT. LUT is lookup tables. Then DSP is digital signal processor. How many digital signal processors they have. Then on-chip memory capacity is given here. Then the arithmetic precision is given in terms of fixed point. Okay. So usually all this design use fixed point. And as you know, fixed point can be used in CNNs. It doesn't cause a lot of harm. So some of them use 8.8. What is the meaning of 8.8? Can anybody guess? Can you guess what is the meaning of 8.8? See the slides and try to guess. And there is another 3.13. Okay, see here. Oh, sorry, we went ahead. Yeah, here. See, it is because 16-bit fixed point. Out of those 16, we have 8-bit for the integer part and 8-bit for the fraction part. That's how it comes to be 16. Here it is 3.30. That means 3 bits for the integer part, 13 bits for the fraction part. So this is how it is written: 3.13 or 8.8. Okay. Now this is the.
What is Q?
Yes. Q, I think, Q is just a notation they have used. Maybe Q refers to quantization.
Okay.
So, and this is the performance for different layers, performance density. That means for each LUT that you have, how much gig operations per second you can perform. For each DSP that you have, how many operations can you perform, and what is the batch size. Now, another thing is we need to carefully optimize the design of FPGA. So actually, FPGA design is quite complex. Any EC student will tell you. So we are not going into actual hardware design or anything. We'll just discuss the principles or key ideas. So designs with same resource utilization may have vastly different performance. Okay, that's the resource utilization is not a good indicator of performance. So here, what is the meaning of resource utilization? So here we see our resources are how many LUTs we have and how many DSPs we have, and of course how much memory we have. Okay, because we are doing the computations using either DSP or LUTs. So it may happen that two designs, they consume the same number of LUTs. Both of them consume 1000 LUTs. But one of them may perform much higher number of gig operations per second than the other. Okay, for example, here you see, let us compare. So here we have, it takes, I think this is the same FPGA. This is not the, this is just the FPGA requirement. So I think here that number is not there. Here that number is not there, but it could happen that two designs, one of them requires 1000 LUTs, another requires 1000 LUTs, but one of them is providing you, suppose 1 teraops, another is providing 1 gigaops only. So that's why just resource utilization is not a sufficient metric. You have to think about other parameters also. Now, parameters of different CNN layers are vastly different, as you know, right? For example, in one layer, you may have kernel size of 3 × 3. Another may have 5 × 5 or 7 × 7. Similarly, image size can be very different in different layers. Number of feature maps can be very different. Okay, so if you reuse the hardware module for different layers, it may lead to poor throughput. So I will discuss one example of this. See, FPGA is what? FPGA is just a programmable logic. Okay, unlike CPU, GPU. So you will reserve. Okay, I want to reserve this much logic. Logic means this LUTs or DSPs. I want to reserve, suppose this 9. That means 3 × 3. right? 3x3 array of DSPs. I want to make a systolic array. So you can very easily do 3x3 multiplication. Okay, fine. But what if your kernel size is 5x5, and then you have to do 5x5 multiplication? Then this 3x3 module is not useful, or it is suboptimal. You will have to break up your 5x5 multiplication into 3x3 multiplication and then do it. So this leads to poor throughput. Okay? Because the computation is mismatched between different layers, and you have to reconfigure it, right? So FPGA, you can reconfigure it. So that's why you will incur the reconfiguration overhead. Also, compute throughput should be matched with memory bandwidth. Otherwise, one of them will become a bottleneck. So we have studied this point before. Where did we study this point? Where did we study this point that this compute throughput should be very well matched with the memory bandwidth?
In AI.
Yeah, we discussed it. Roofline model in arithmetic. Yeah, there we discussed, right? So memory bandwidth. If you have too much memory bandwidth, but your compute capability is very less, you can't get much performance. If you have very little memory bandwidth, but you have huge compute throughput, then memory will become a bottleneck. So this point, please don't forget. Okay. Now another thing is the tools for developing neural network models with CPU GPUs. They are already mature. Why? Because CPU GPU means we are doing high level programming. You don't have to too much think about the low level hardware. Whereas on FPGA, you have to think about the hardware also. So that's why designing tools for FPGA takes some time. Okay. So the same tools can't be directly used in FPGA. That means first somebody does the research on GPU, then you have to port that research ideas or port those frameworks on FPGA. That takes some time. Okay. And neural network models are evolving so fast that even if you want to do some work on FPGA, you are late, right? If you're delayed by 2-3 months, by that time, so much more research has happened, and you're always left behind. So this ability to quickly program, that is very much important in a fast-changing field like deep learning. So even with HLS means high-level synthesis tools. So there are actually like broadly two types of tools. One is HLS. For example, you can write your code on C++ or C, and that will get programmed into FPGA. Another is you write RTL, register transfer level, which is really core binary, very register transfer notation and so on, which is very low level of programming. So even if you're not using register transfer level, even if you're using HLS, high level synthesis, even then it takes multiple months, right? For example, if I were to ask a PhD student to work on FPGA, maybe their PhD may get delayed just because they chose FPGA. Right? They also have to graduate. So that's why the point is, if it takes a lot of time, then your company may not be able to wait for that much time. All right. That's why an FPGA-based design may not efficiently model the most recent neural network algorithm. Okay, that's why you may be left far behind. If it takes, like, suppose the delay between GPU development and FPGA development is 5 months, that's just too much time in deep learning. Also, compared to FPGAs, GPUs provide higher performance with much lower design effort, because GPU is like there's a high-level programming. For example, in whatever in TensorFlow, what we can do with just suppose 10 lines of code. In FPGA, if you want to use it using RTL, it may be so many lines of code, and it's so many months. Like the same, a designer may have to spend one month. The GPU will also give you higher performance. Then what is the benefit of FPGAs then? If GPUs can give you less, faster code with less design effort, then why we should use FPGA at all? What is the benefit of FPGA? Gaurav Verma, you know it, right? Yes.
Yes, sir.
What is the benefit of FPGA? Tell me, you know, right? What is the benefit?
Sir,
Why do you use FPGA?
Yeah, it is quite easy to program and quite quickly to implement our logic or algorithm, whatever we are going to design.
No, compare. See, it is easy, but compared to GPU, it is slower, right? Nowadays, it is slightly easier compared to what it was previously. But still, compared to GPU, FPGAs are difficult to program, right? So why? So my question is, why do we use FPGA at all? It's so difficult to. What is the benefit of FPGA? Anybody else? Imkan?
Sir, we can reuse it.
No, GPU also you can reuse it, right? It's not ASIC. GPU also you can reuse.
Sir, I think cost effective, sir.
Cost. See, FPGA is also costly, GPU is also costly.
Sir, memory, FPGA is low memory.
Yeah, that is true. So that is you're telling the disadvantage. I want to ask what is the advantage of
maybe the space required on the board, so that might be one of the constraints.
Space.
Yes, the space required on the boards. When we implement FPGAs, generally the space required for the complete implementation of the whole project. So maybe less when you compare with GPUs and other this thing.
So, see, FPGAs are not cheap. If you want to purchase FPGA, it's not cheap. Let me tell you, it's not cheap. But what I'm asking is, what is the plus point of FPGA?
Sir, in FPGAs, we have this advantage of having that partial reconfiguration also.
No, GPU is fully, GPU is anyway, GPU is software programmable. So it's fully, it's not like ASIC, right? In GPU, you write one code today, just after 2 minutes, you write another code. What's the harm? It's not like ASIC. ASIC is fixed logic. So this advantage what you're telling of FPGA, that is over and above ASIC. It is not over and above CPU or GPU.
Sir,
CPU,
energy
GPU,
efficiency.
Yes,
Sir,
Energy efficiency.
Yes, that is the main reason. Yeah. Gaurav, what you wanted to say, Gaurav Anjan?
Sir, the latency is low, sir, and that is the reason it is utilized in a deep learning.
Yeah, actually, latency is low, but actually GPU is usually lower.
FPGAs are much more power efficient, sir.
Yeah, so Anubhav said, yes. People who have CSC, EC background, they may probably have some insights. Yeah. See, the main point you have to remember why we are discussing if FPGA has so much limitations or challenges, why bother about FPGA? Especially the biggest point actually is this. At least for somebody who is not from EC background, right? Suppose you are you know a lot about deep learning, but now you need to decide, should I work on FPGA or GPU or CPU or ASIC? Then at least first you want that it should not take too much time. Otherwise, your boss will remove you, right? So now you join some company, you need to design some accelerator, choose. You need to make recommendations to your company which platform we should choose. So that way you have to think. So here, this is a very, very big limitation. But the benefit of FPGA is that energy efficiency is high. So that's the idea. So please remember this point. And of course, if you really optimize it well, then it may happen that for the same cost, right, your throughput may become higher on FPGA, but usually it's not higher. Usually GPU gives you high performance. Okay. Now there are 4 types.
How it is energy efficient means even it has a very less amount of memory onboard memory.
Yeah. Because
so
actually,
the data movement will be more, no?
Data movement will be more, but your point is correct. You're doing research in that area. Okay. So see the point is actually GPU is still a general purpose processor. It is not as general purpose processor like a CPU, but still it is somewhat general. So it has a lot of things. Whereas on FPGA, you are implementing only what you need. Right? Suppose if you need compute, you will just implement compute. Whereas GPU will also have a lot of scheduling logic, this logic, that logic, which you may not need. Not everything which GPU is providing you may use. GPU may have massive resources, but you may end up having only 20% of the peak throughput, just as we saw in the roofline model. So you are getting only 20% of what GPU is able to offer, so that 80% still consuming energy or power. That's why its power will be high. Whereas on FPGA, even if your FPGA board is very, very large, but you may be using only 20%, then only 20% is getting powered on. Remaining part is not getting consuming energy. Fine?
Okay, sir.
So now this is 4 types of resources on Xilinx FPGAs. There are other like Altera. So they may have slight differences, but that's fine. So here we have DSPs, which is digital signal processor, LUTs, lookup table, flip-flops, and block RAM. Block RAM is just RAM. It's just like we say SRAM, but it is specifically called block RAM. I don't exactly know the reason, but it is called block RAM. It is just similar to the SRAM. Okay, so DSP is an ALU which can perform logic and add, subtract, multiply operations. A DSP slice can implement a MAC operation. So now you know why we are highlighting MAC. Can anybody, Arghya or Ashish, can you please tell me why we are specifically mentioned MAC operation? Kunal, Mohit, Narendra. See, actually, there is a very, very famous story of Alexander the Great, right? He would first conquer, say, for example, he will in Delhi, then he will go to Kabul, then he will go to maybe Tehran. And while he will go to the next city, he will lose the previous city. That means some other attacker would come and win the city from him. So we should not be like that, right? As we are going to next lecture, we should not forget the previous lectures, right? So try to make a connection. Why did we specifically mention MAC when we already mentioned add and multiply? Let us see if we can correlate. Yes, Narendra.
It can perform in one cycle both operations.
No, but why MAC operations are important? Tell me. How, whether a slow or fast, that could have been consideration somewhere, but not here. But tell me what is the special significance of MAC operations? Anyone else, please?
Sir, vector operations, matrix
Sorry?
multiplication. Sir, vector operations, matrix multiplication and all.
Yeah, but yeah, there are some, yeah. See, the whole point is MAC operations are very useful for this. Yeah, matrix, vector operations and matrix operations, which are used for neural networks. So our goal is how we can use FPGA for neural networks. Probably this point was quite obvious, but you have to keep it every time. Whenever you're reading a paper, okay, immediately form the connection. Where does it fit? Okay, in Xilinx FPGA, DSP slide is termed as DSP 18 because it can perform up to DSP 48 because it can perform 48-bit addition. LUT can implement a combinatorial logic operation. And DRAMs, they are used for on-chip storage. Now, FPGAs work at low frequency, as we showed, between 100 to 500 megahertz. They depend on massive parallelism for achieving high throughput. Okay, so now we'll discuss some techniques for optimizing deep learning on FPGAs. And in the next lecture, we'll discuss the Microsoft's brainwave architecture. Okay, so first thing is, as you saw in the previous slide that I showed here, most works, they have implemented fixed point. Okay, because see, first of all, FPGAs are used primarily nowadays only for inference. I'm not sure if they are doing a lot of training on FPGA, but mostly FPGAs are used for inference. Because as you can see, because it does not have a lot of resources, bandwidth is less, and so on. So and its power consumption is also less. So that is very ideally suited for inference. Okay. So recent FPGAs have many DSPs which implement multiplier, pre-adder, accumulator core. This is FPGA terminology, this core, processor core. So that means they can do these operations, multiplication, addition, accumulation. So here we are showing that compared to 32-bit floating point, if you were to just do fixed point operations and also reduce the bit width, it greatly reduces the resource consumption. Okay, so here are 3 examples. First of all, let us just focus on this Xilinx. Let us ignore these 2 sites. So here we are trying to implement a multiplier. Okay, using only LUT and flip-flop. We are not using DSP. Here, first go, we are not using any DSP. We are just implementing either a multiplier or adder using an LUT or flip-flop. So if you were to implement FP32 multiplier, it would require 708 LUTs and 858 flip-flops. But if you implement just fixed point 16-bit multiplication or multiply, we only need 289 LUTs and 301 flip-flops. Especially if you go to adder, here we need 430 adders and almost 750 flip-flops. But that requirement reduces to just 16 LUT and 16 flip-flops if we are working with fixed 16. So that's a really, really huge advantage, isn't it? And now you come here. Now we are also allowed to use DSP. So if we just implement FP32, we need 800 LUTs, 1284 flip-flops, and 2 DSPs. But if we go to fixed 16, we can do all this with just one DSP. So such a huge saving of resources we get here, isn't it? We don't need to use any LUT, we don't need to use any flip-flops. All of that with just one DSP. So that means, especially on FPGA, working with lower precision is much more useful than it was probably on GPU or CPU. Okay, is it clear? This point, any questions on this? You don't have to remember this number. This is just for kind of example. Okay, fine. Okay, let us go on. Similarly, here this is Altera. In Altera, they have this ALM, which is Adaptive Logic Module. I don't know what is the relationship between ALM and Altera. It must be some kind of logic. So here again, these numbers are given, and as you can see, if we go to lower precision, we can do the same thing with much less number of resources. Now, next thing is, here you observe one point that coming from floating point to fixed point gives you advantage, and coming from 32-bit to 16-bit gives you advantage. But when you go below 16, for example, 16 to 8 or 16 to 4, there is no additional advantage. Fine, right? Going from 32 to 16, you have advantage, and going from floating point to fixed point, you have advantage. But how can we achieve the advantage if you want to go further from 16, we want to go to 8 and towards 4? How to have further resource saving? So for that, here, that is the same point that they have observed. There is no extra benefit on using 4-bit or 8-bit because you still have to use the whole DSP. That means wide multipliers and adders remain unutilized. So that's why here is the idea. Implement 2 narrow fixed point multiplication with a single wide fixed point multiplication. So how do we do it? Let us see. So I will come back to the slide. Let me first discuss the example. So suppose we want to multiply 2 numbers. One is A into B and another is A into C. So here the constraint is that one of the operands have to be similar. Let me say, for example, A is similar. Okay, so we can implement it as A, then this left shift B by K bits plus C, where we assume that B is K bits wide. If K is very large, then output of AB and AC don't overlap and they can be easily separated. Okay, let me take this example. So here, see, suppose we have to multiply. Here it is A into C and B into C. So here C is common. In this one, actually A was common, but here C is common. So suppose here A is getting multiplied with C and B is also getting multiplied by C. So one option is that I first do B into C and then I do A into C. Okay, fine. Now, but here what I do, I create a single number, which is A, and left shifted by so many bits, and in between we insert 0, so many zeros. So here with a single multiplication, here I will compute B into C, that will come on the least significant bit side, and A into C, that will come on the upper bits, most significant bits. Fine. So here is an example. Suppose I want to compute 1100 into 1101. So that is answer is here. And whatever is the multiplication 1001 and 1101, that answer comes here. Fine. And in between, they have a 0 bit, which is the guard bit. So please remember this formula. I will give some questions based on this. So to perform two n-bit multiplications, simply why? Because we are simultaneously doing two things. Operation is same, multiplication, but operands are different. We need 3n plus 1. So here you can see 3n plus 1 bit. At least we need 3n plus 1. That means this multiplier can multiply two numbers. One of them is 3n plus 1 bit. Another of them is just n bit. For example, if we have this multiplier, right, 25 into 18 bit multiplier, then n can be at most 8. Why? Because see this, you put n equals to 8 here, so this reaches 25. We can't go above 25 because our multiplier is 25. Although we can increase n here, this n can go up to 18 and we are only at 8. But because we have reached this limit, 3n plus 1, that means this number is already, we have reached the limit. That's why maximum n that we can do is 8. That means using this multiplier, we can do two multiplications. Each of them is multiplication by between 8 bits and 8 bits. So now let me come back to this. So here, two 8-bit multiplications are implemented with a 25 into 18-bit multiplier, k equals to 9. So you need to shift it by this many bits. So here this n plus 1 is 9. N plus 1 is 9. Actually, you need to also take into account this n bits also, but that is implicit. That's why they did not write it. So now let me read it again. So we can implement two narrow fixed point multiplication. One of them is 8 into 8. Another of them is also 8 into 8. But we have a single multiplier, which is very wide, a single wide multiplier. So we can implement these two multipliers with a single wide multiplier. Okay. So if we can sufficiently left shift it, then output of AB and AC will not overlap. That can be easily separated. Any question here? Please feel free to ask. I will give one question based on this.
Sir, here when we are multiplying A into C,
yes,
in the example, so the result is not 8 bits, sir. Means,
it will be 2 in bits.
so it should be 8 bit for the example. The example that you have shown here.
Okay, I think see here, these are just the input. These are just the width of the input. Output will be more than this.
No, sir, that one, the 11101, and there is a guard bit.
Yeah, guard bit is unnecessary. Guard bit you could have avoided.
Before guard bit, it should be 8 bit result, na?
So you're saying this part?
No,
This part.
Yes.
Okay, let me try to see. So here you're saying this is 8 bit.
But here it is showing only 7 bit. Result should be 8 bit.
See. That actually depends on the number. If you multiply 1 with 1 1 1 1, that this number is up to 8 bits. It could be less. Then you multiply 4 bits with another 4-bit number. Your answer could be up to 8 bits. Right?
Yeah, maximum bit that we will get is 2n.
Yeah, maximum is 2n. Yeah, maximum is 2n. Maximum is 2n. Yes. Any other question, please? Okay. Now we'll discuss binarized neural network. So instead of 32-bit floating point or even 8-bit fixed point or integer weights at all, we just directly come to 1-bit values. That means our weights are 1 bit and our inputs, or what we call input activations, they are also 1 bit. So in this way, we can drastically reduce the memory capacity and bandwidth requirements. And binarized data has higher cacheability. It's easy to cache binarized data, which is good because FPGA has low memory capacity. For example, here, 8-bit fixed point and binarized LXNet, they require 50 megabytes and 7.4 megabyte memory respectively. So So that's why, because see, that means binarized LXNet requires only 7.5 megabyte and 8-bit fixed point requires 50 megabyte. So that's why binarized LXNet can be fully stored in the on-chip RAM of FPGA. Because it only requires much less, right? Compared to 50 megabytes, 7.4 megabyte is much less. Sorry. So that's why on a typical FPGA, this fixed point neural network becomes bound by memory bandwidth, whereas BNN, here, see, as you can expect, with BNN, we can our arithmetic intensity can be much higher, right? Because we are fetching very less weights and we are doing the same number of operations, so arithmetic intensity becomes very high. So we can reach the peak of the computation performance. This point is very obvious if you remember the roofline model. Here is an example. So one thing, please remember. So when we say binarized, usually when we say binary, it is 1 and 0, right? Binarized, binary just we mean 1 and 0. But see, the point you have to understand, our weights are either -1 or +1. And when we represent them, that means when we store them in the memory, we will represent -1 with 0 and 1 with 1. Okay, so when we store a value 0, it doesn't mean that the weight itself is 0. Our weight is actually -1. But we are representing it as 0. Fine, please remember this point. That will be clear. Okay, now let us see how. So suppose we have this input, right? -1 +1 +1, and here this is the input. So you can do very easily the matrix multiplication. So this is -1 +1, then 1 1. So that is this number. Then this multiply with this, with this, with this. So that is this number, which gives us this, and then this number, this gives us this. Fine. This is the binarized matrix multiplication. So now here we have actually done the matrix multiplication. Now, what our claim is that when we just have binarized multiplication, that means both inputs and weights both are +1 -1. That means both are binarized. Then we can convert this multiplication operation, multiplication and addition. See, here additions are happening, right? And here multiplication is happening. So we can convert this MAC operation into just XNOR operation and population count. So now, first of all, let us see how we can do that, and then I will tell you why it is advantageous. Advantage is already mentioned here. Instead of DSP blocks, we can just use XNOR gate. But I will come back to it. First of all, let us see how we actually do it. So now let us see. We represented -1 with 0 and +1 with 1. Okay, this correspondence you have to remember. This 0 doesn't mean the actual weight is 0, but it just means the weight is -1. So now we first of all do XNOR operation. So everybody knows what is XNOR. Everybody knows what is XNOR. Gaurav, you know, right? XNOR operation.
Opposite of OR.
Opposite of OR.
OR.
Opposite of OR is NOR. Opposite of OR is NOR. What is XNOR?
Opposite of XOR.
Opposite of
XOR operation.
Yeah, very good. And what is XOR then?
Dissimilar output, dissimilar inputs leads to output 1.
And similar inputs lead to what?
0 for XOR.
Yeah. Okay, so let us first compute the XOR between this. So first of all, let us see. See, we have 0 1 1. So that is 0 1 1, 0 1 1, 0 1 1. Okay, and we have this 0 1 1. We have this 0 0 0 here, and we have this 1 1 1. So that is 1 1. So first of all, we'll compute the XOR between them, and then I will compute the XNOR. So here 0 1 1, 0 1 1. So both of them are exactly same. So it will be 0 0 0. And so that is XOR. And because it is XNOR, all of it will become 1 1 1. Okay. And bit count just means that we just count how many ones are there. So here we have 3 ones. So that's why the answer is 3. Okay. Now let us compute the second one. So here we have 0 1 1 and 0 0 0. So how many of them are dissimilar for computing XOR? How many of them are dissimilar? Out of the 3, how many bits are dissimilar?
2 bits.
2 bits are dissimilar. Okay. So the output of XOR will be 0, 1, 1. Fine. Is the output of XOR. Now you have to invert it to get XNOR output. So that will be 1, 0, and 0. Okay. So this 0 corresponds to what? Minus 1. Right? This 0 corresponds to minus 1. So it will be 1 plus minus 1 plus minus 1. So what is this answer? What is this?
Minus 1.
Yeah, minus 1. Please remember this computation because I will give this in a homework. That's why I'm doing it in detail. Now let us see the last one. So here we have, out of the 3 bits, how many bits are dissimilar?
1 bit.
1 bit. So that's why it will be 1, 0, 0. And then if you invert it, it will be 0, 1, 1. So because 0 equals to minus 1, so we have minus 1 plus 1 plus 1. And what is the answer?
Plus 1.
Yeah, plus 1. So that here is the answer. Okay. So this is the answer that gets stored. So now you can see this. First of all, these 2 operations are equivalent, at least for this example. So now see, if you want to do actual multiplication and actual addition, why do you want to use a full multiplier if all you have to do is just 1 bit multiplication? See, a usual multiplier will do 18 bits, as we saw, 25 into 18-bit multiplier. So using such a wide multiplier to multiply just 1 bits, is it worthwhile to use a full multiplier? No, right? So better to do it using XNOR. XNOR is anyway a logic binary, by binarized logic gate, which just takes 2 inputs, right? So that's why instead of DSP, you can just use XNOR. So instead of DSP blocks, if you can use XNOR gates, it is very, very advantageous. That is the whole advantage. So that means, especially on FPGA, it is much useful to execute a binarized neural network. And then further, a bit count can be realized using LUT. So FPGAs have a lot of lookup tables. So whenever you have this input pattern as 0, 0, 0, 0 means minus 1, 0 means minus 1. So this will become minus 3. Similarly, right now, please ignore this. Please ignore this part. For now, just see 0, 0, 1 is minus 1, minus 1, 1. That is minus 1. For example, here it is plus 1, minus 1, minus 1. This becomes minus 1. Here it is plus 1, plus 1, plus 1. It's going 3, plus 3. Okay. So now if you know 2's complement representation, then you will find out that this is equivalent to this. If you don't know 2's complement, it's okay. I will not try to discuss it now. You can just ignore this part. As long as you can understand this part, that is fine. Okay, if you can just understand this part, which is quite easy. If you just subtract, if you just replace 0 with minus 1 and 1 with plus 1, then you can easily get this number. And if you know 2's complement representation, you will find out that this number is actually minus 3. This number is actually minus 1. Okay, so the whole point is now you can replace MAC operation with XNOR gate and population count. This XNOR operation you can implement using XNOR gate, and this population count you can implement using lookup table. So in this way, instead of DSP, you can just use XNOR gate plus lookup table. So you get huge reduction in area and energy. And also because FPGAs have plenty of them. Because after all, FPGA is programmable logic, and we have done our calculation just using logic without doing arithmetic operations. So that's why FPGAs provide native support for bitwise operations. That's why BNNs can be implemented efficiently. Now we'll compare FPGAs with GPUs if we are implementing binarized neural network. Okay, so let us see this. So here we are comparing FPGA with GPU for reduced precision neural network. Okay, So if you have any questions till this point, please ask me, and we'll give you some example questions based on this. That's why please pay careful attention. Okay, if you have no question, let us go for it. So here, first of all, we will take example of a CNN which uses fixed point notation, fixed point weights. And then in the next slide, here we will do that. Okay, not just fixed point. I want to just go to binarized neural network, BNN. Fine. So first of all, let us see this. So here we will compare two devices. One is FPGA, one is GPU. So this FPGA has 3600 DSP48 units. It has so many, more than 4 lakh LUTs, and its operation frequency supports just 100 megahertz. Whereas here it has 3000 cores, and every core has 1 ALU, suppose, and its frequency is 1 gigahertz. Now you can assume that suppose a DSP unit can do one fixed point operation, as we have shown in the table. And you can also assume that one CUDA core can do 1 MAC operation in each one cycle. Okay, so here you can see the number of compute unit. Here it is around 3600. Here it is around 3000, which is comparable, not much different, same ballpark. So that's why they have comparable concurrency. That means they have similar number of compute units. But because frequency of FPGA is 10 times lower, see, this is 1000 megahertz, whereas here it is just 100 megahertz. That means 10 times lower frequency of FPGA. So because FPGA frequency is so low, that's why its throughput will also become low. Okay, its throughput will be maybe 1/5 or 1/10 of the GPU throughput. Is it so? Here the point is LUTs are not utilized. We're not able to use LUTs because with fixed point we can't use LUTs. We are just using DSP units for doing computation. Okay, now let us see second case. In second case, we are implementing binarized neural network. So here a CUDA core can perform suppose 32 bitwise operations in a single cycle. This is our assumption. So that we are giving sufficient advantage to GPU that a single CUDA core can perform 32 bitwise operations in each cycle. So that's why now the throughput of GPU will go high by 32 times. Fine. Okay. Whereas on FPGA, now you're doing bitwise operations, they can be executed even using LUTs. So previously we were not able to use these LUTs, which were too many. See, FPGAs has too many LUTs, lookup tables. We were not able to use them. Now let us try to use them. Assume that a 6-input LUT can perform 2.5 XNOR operations. Each of our LUT is suppose 6 input, and suppose each LUT can perform 2.5 XNOR operations. So that's why Vertex 7, this FPGA that we are discussing, that can give us 1 million-fold parallelism, right? Because we multiply 2.5 with the number of LU lookup tables. So if you account for frequency difference, because although FPGA has higher amount of parallelism, but it also has 1/10 the frequency. So if you also take into account the frequency is lower, now this number, that means you divide this number by 10. So once you divide this number by 10, because of the frequency, this number becomes comparable with this number. So this is a very, very simplistic model of FPGA GPU that through this we have shown that now FPGA and GPU can provide similar throughput for the binarized neural network. Whereas for reduced precision, that means even for fixed point neural networks, GPU will definitely provide you higher throughput than FPGA. If you have any question, please feel free to ask, because we will definitely give you one question like this in the homework or exam. Try to see what we are doing. In the fixed point case, we used only DSPs. We did not use LUTs. That means we had a lot of resources, but workload was not able to make use of those resources, so it was going waste. So that's why the performance was coming out much poor for FPGA. Now, when we come to binarized neural network, this workload is such that it very well matches the characteristics of FPGA. Fine. So that's why it has the benefit that now for binarized neural network, at least for this example that we have shown, FPGA can provide you much better performance, and for this example that we'll discuss, that performance could be comparable with the GPU performance. Any questions? No. Okay, we'll go forward. Now there are some challenges of BNN. Here actually what happens in the first and last layers, because we are interface, because see our original image that will be specified in floating point, 32-bit floating point, and last output also has to be floating point. So both so that means in the first and last layers we have to deal with floating point numbers, even though intermediate layers will be just processing binarized value, but at least the first and last layers have to deal with binary the floating point numbers. So overall your accelerator has to deal with both binary and floating point numbers, which increases complexity. Okay, so this is one technique. Now this is one research paper based technique. If you will